Okay, so we are finally ready to start understanding some of these paradoxical properties of entanglement. In this video, we'll talk about what's called the EPR paradox, which was invented by Einstein, Podolsky, and Rosen. So this paradox starts by understanding the Bell state a little more closely. So remember, the Bell state was an entangled state of two qubits, where they were in an equal superposition of being in the state 0, 0 or 1, 1, meaning that the two electrons are both in the ground state with amplitude 1 over square root 2, and they are both in the excited state with amplitude 1 over square root 2. Now, it turns out that if we were to write the state of each electron in the plus-minus basis, then this state can also be expressed in a different way. It's the two electrons are with amplitude 1 over square root 2, they are both in the state plus plus. And with amplitude 1 over square root 2, they are both in the state minus. So let's see how we show that. It's actually very simple. So we'll just write out the state 1 over square root 2 plus 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 1 over square root 2 minus minus, which is what? Well, what's the plus state for the first qubit? It's 1 over square root 2, 0, plus 1 over square root 2, 1. Plus state for the second qubit, it's the same thing. And what's the minus state for the first qubit? It's 1 over square root 2, 0, minus 1 over square root 2, 1. And for the second qubit, it's the same thing. Okay, so now let's expand it out. So what would we get? We'll get a superposition of 0, 0, 0, 1, 1, 0, 1, 1. So we just need to collect coefficients and see what we get. Okay, so there's a 1 over square root 2 outside, so let's just leave it outside. And now, what's the amplitude of 0, 0? Well, we get two contributions. We get one contribution from here, which is 1 over square root 2 times 1 over square root 2, which is a half. And we'll get a similar contribution from here, which is another half. So we just get 0, 0. What about 1, 1? Well, we'd get a half contribution from here. And here we get minus 1 over square root 2 times minus 1 over square root 2. So again, a half. So we get a full contribution of 1 for 1, 1. But what about 0, 1? Well, we'll get a half from here, 1 over square root 2 times 1 over square root 2, and minus half from here, 1 over square root 2 times minus 1 over square root 2. And similarly for 1, 0, we get plus half, minus half, so it all cancels. And so we are left with exactly the Bell state, 0, 0 plus 1, 1 times 1 over square root. Okay, so let's try to understand what all this means. So remember, we said last time, we get the two qubits to interact with each other, they get into this Bell state, into this entangled state, and now we can move them far apart from each other, and they stay in the Bell state. So if you were to measure the first qubit, and it happens to be 0, we know that if we measure the second qubit, it'll also turn out to be 0. Similarly, if the first one turns out to be 1, the second will certainly turn out to be 1. But then we said, maybe this is not so paradoxical after all, because when these two qubits interacted with each other, maybe they, with 50% probability, they both went into the state 0, 0. And with 50%, they chose the state 1, 1. So that even after they were moved very far apart, if we measure the first one and it turns out to be a 0, the second one will also turn out to be 0. So what's so paradoxical about that? Well, now we get to measure not only in the 0, 1 basis or the bit basis, but also in the sign basis. And if we choose a sign basis and the first qubit is a plus, actually the probability it'll be a plus is a half, probability it'll be a minus is a half. But again, if we see the first qubit in the state plus, the second one most certainly will be in the state plus. If the first qubit is in the state minus, the second one most certainly will be in the state minus. Okay, so this is the basis of the EPR paradox, which Einstein, Podolsky, and Rosen formulated in 1935 to express their dissatisfaction with quantum mechanics. So it's a very clever paradox. So what Einstein, Podolsky, and Rosen said is, suppose these two qubits are very far from each other, so that you know that even light would take an enormous amount of time to go from one to the other. So now whatever you do to the first qubit cannot affect the second qubit, at least for a very long period of time. Okay, so now you can choose to measure the first qubit either in the bit basis or in the sign basis. If you choose to measure it in the bit basis, then you know exactly what the bit value of the first qubit is. But then, because of the nature of the Bell state, you also know the bit value of the second qubit. If you choose to measure the sign value, then you'll also know the sign value of the second qubit. So whichever one you decide to measure, you'd know that value of the second qubit. But now here's the interesting thing. The second qubit is not affected by which one you decided to measure, which of these two values you decided to measure. And so Einstein, Podolsky, and Rosen argued that what this means is that both values of the second qubit must be determined. They must already be present. And so this seems to contradict the uncertainty principle. So what it says is, even though it's true that if you measure the bit value of the first qubit, it disturbs the sign value, but the second qubit is so far away, that measuring the bit value of the first qubit doesn't change the sign value of the second qubit. And so they seem to have gotten past the uncertainty principle. And so what Einstein, Podolsky, and Rosen concluded is that quantum mechanics is an incomplete theory. So when it tells you that you cannot know both these values simultaneously, what it's saying is you cannot know the value simultaneously in quantum mechanics, but they believe that behind the scenes, in actual fact, nature actually defines all these values. All these physical quantities are actually determined. And that quantum mechanics somehow is an incomplete theory that limits the amount of information that we can get about nature. And so Einstein spent the last 20 years of his life searching for such a more complete theory. He failed in his attempt. Quantum mechanics, of course, says that the state of the second qubit is not defined by itself because it's entangled with the first qubit. And so saying that the bit and the sign value of the second qubit are well defined it just doesn't make sense. In the next lecture, we'll see even more interesting properties of entanglement. And we'll see that there's more to be learned about entanglement that if only Einstein had known, he'd have saved 20 years of effort.